Hello and welcome to this Vivado quick take video. In this video, we'll be putting together a simple MicroBlaze design in the IP Integrator tool. We will use several IP blocks such as the proc sys reset, microprocessor debug module, clocking wizard, AXI interconnect, some local memory, an interrupt controller, a gpio, and a uart light code. Then we'll take the design through implementation and generate bitstream. We will then export the hardware to SDK and write a simple Hello World application code which we will run on the Kintex 7 KC705 board. We start our design by launching Vivado and creating a new project from the Getting Started page. We name the project MicroBlaze Design and go through several screens that present various options to set up our project. We change the target language to VHDL, although we could have left it at its default value of Verilog. We select boards in the default part page. Vivado is board aware and it knows the physical connections present on our target board. It can thus generate the appropriate physical and timing constraints for our target board based on the interfaces that we choose in our design. We select the KC705 target board here. Review the summary screen to make sure that all the options have been entered correctly and click Finish. Now that the project is created, we'll put together our design in the IP Integrator tool. To do this, we start by clicking on Create Block Design and enter the name of our block diagram. The IP Integrator opens up in a new canvas. Maximize the canvas so that we can have a nice big area to work in. Next, we'll instantiate the MicroBlaze processor in our design. To do this, right-click anywhere in the canvas and select Add IP. In the search field of the IP Integrator catalog, type in the first few letters of the MicroBlaze, select the MicroBlaze IP from the search list, and hit Enter. For a processor-based design such as this, IP Integrator offers assistance to the designer by offering something called a block automation. We select the Run Block Automation link in the ribbon on top of the IPI canvas. This will pop up a Run Block Automation dialog box which presents us with several options for configuring our design. We select the appropriate options for our design and click OK. The Block Automation wizard configures our design based on the selections that we have made. Next, we add a couple of other IPs that are typically used with a microprocessor-based design. These are the gpio and the uart light core. IPI also offers something called connection automation. This is another form of designer assistance that can be used to connect the unconnected IPs to the MicroBlaze processor and the input-output port of the design to the physical pins on the KC705 target board. We click on Run Connection Automation and select the interfaces that we want to run connection automation on. We connect the reset pin on the proc sys reset block to an input reset source on the board. Then we connect the clock pin of the clocking wizard to an input clock source on the target board. Next, we can connect the slave port of the GPIO core to the MicroBlaze processor via the AXI interconnect. We then connect the GPIO LEDs to the LEDs present on the board. Likewise, we can connect the interfaces on the uart light core. Next, we need to connect the unconnected pins of the concat IP. One of the interrupt sources is the interrupt output from the uart light. We connect this input of the concat block to the interrupt output of the uart light core. The other input of the constant block can be tied to ground. To do this, we instantiate a constant block and configure it to output a value of 0. Finally, we need to connect the reset pin of the clocking wizard to the input reset port of the design. Once the design is complete, we can click on Regenerate to obtain an optimal placement of our IPI block diagram. Then we select the Address Editor tab and inspect the memory mapping to ensure that all slaves have been mapped properly. IPI automatically maps the peripherals as they are placed in the design. However, we can change the memory mapping as we desire. In this case, we'll go with the default mapping. Next, we need to run the design rule checks on the design to make sure that our design is free of any errors. To do this, we click on Validate Design on the toolbar. Validate Design shows that there are no errors in the design, so we can go on to generate the output products, which include the source for the IP blocks in our design and necessary physical and timing constraints. To do this, we right-click on our block diagram and select Generate Output Products. Once the output products have been generated, we need to create a top-level HDL wrapper that will instantiate our IPI block diagram. We can do this by right-clicking the block diagram and selecting Create HDL Wrapper. Now we are ready to take the design through implementation and generate the bitstream. We do this by clicking on Generate Bitstream in the Flow Navigator. Vivado starts synthesis, optimization, placement, and routing on the design. You can monitor the progress of each of these steps by looking at the top right corner of the Vivado window. Once the bitstream has been generated, we can open the implemented design and look at various reports such as the timing report. To do this, open the implemented design. Once the implemented design is open, expand the implemented design folder in the Flow Navigator. Click on Report Timing Summary. Make sure that the design meets all the timing constraints specified by our constraint set. The next step is when we export our hardware design to the Software Development Kit or SDK, where we can create our application code. To export the design, select File from the menu and select Export Hardware for SDK. This will export the list of peripherals in our MicroBlaze design along with their memory mapping information over to SDK. When we select the Launch SDK option while exporting hardware, SDK launches in a separate window. So SDK has launched and we can go on to create a new application code. We do this by clicking File from the menu option and then selecting Create New Application Project. We type in the name of our project, Hello World in this case. Click on Next. Then select the Hello World template from many of the templates available in SDK. SDK automatically compiles and builds the project for us. So we need to make sure that our board is powered on before we can program the FPGA. So we'll click on Xilinx Tools and then select Program FPGA from the menu option. In the Program FPGA dialog box, we need to make sure that the location of the bit stream is correct, and then we hit Program. This will program the FPGA with the correct bit stream. Now we are ready to launch our code on the MicroBlaze processor. However, before we do that, let us set up our terminal so that we can monitor its output. The terminal is connected now and we are ready to launch our application code. We execute the code by right-clicking on the target debug agent and selecting Resume. And there you have it. Hello world.
Thanks for viewing this quick take. If you found this video useful, you might be interested in taking some of our more in-depth